Hello, welcome to another module in this massive open online course. So, we are looking at various applications of this paradigm of least squares, that is the different applications where least squares can be employed, and in general least squares is a very flexible and powerful paradigm, and can be applied in a variety of scenarios. In this module, let us look at another interesting application, and that will be in the context of image processing, specifically in the context of image deblurring. Okay. So, you want to look at yet another interesting application, and in fact there are umpteen number of applications of the least squares paradigm. So, just to illustrate the versatility of this framework, let us look at an application in the context of image processing, okay, specifically in the context of image deblurring. Okay. So, we want to look at the deblurring of image. Now, just before we formulate the mathematical problem, let us just look at the physical relevance of this. What happens is, when you are trying to capture the image, let us say you are trying to make a figure of a person over here, and when you try to capture an image of a person, and so this is an impression of my camera, and I am trying to capture the image of this person. And now, if this person or if this object is in, let us say, so this is basically image capture device, which is your camera, or can be in fact this can be extended to the context of videos also. So, this is not necessarily applicable only for images, but can be applied also for videos. If this object which you are trying to image, or whose image you are trying to capture, is in motion, then this leads to a blur. Alright. So, this, remember, when you have, typically you might have seen, in fact the blur effect that is artificially applied, for instance on things, typically on the images of, let us say, cars or vehicles that are captured, to give the impression that something is in motion, that an object is in motion, and when the object is in motion, that naturally gives rise to blur. So, the blur effect is basically associated with motion, and blur can also, it's basically a degrading effect of an image, and can also arise from several other factors, such as environmental factors, atmospheric factors, motion of the wind motion, etc. So, in general, motion leads to blur, and this is termed as motion blur. Okay. Motion is one of the predominant causes of blur, and therefore, to get a clean image implies image has to be deblurred. Now, one way to model the motion blur is the following. Let us say you have the output pixel y of k. So, the model for blur model, let us look at it. The blur model can be described as follows. Let us say you have an output pixel y of k, that can be described as L equal to 0 to L minus 1. The input pixel, or the blur kernel h of L times x of k plus L. Okay. So, let me just write this equation down. For instance, we have y of 0 equals h of 0 x of 0 plus h of 1 x of 1 plus h of L minus 1 x of L minus 1. Okay. And you can also write this as y of 1, or you can make this, that is fine, it does not matter. You can write this as y of 1 equals h of 1 times x of 0 times x of 1, or let me just write this as follows. I can write this as h of 0 times x of 0, y of 1 is h of 0 times x of 1, just to make this system causal, although it does not matter, it does not really matter because image processing can be non-causal. So, this is h of 0 times x of 1 plus h of 1 times x of 0, and I can write y of 2 equals h of 0 times x of 2 plus h of 1 times x of 1 plus h of 2 times x of 0. You can take the past pixels here to be 0. So, you can write this as h of L x of k minus L, and you can assume that the past pixels, for instance x of minus 1, x of minus 2, so on, equals 0. That is, this is a causal signal, that is, this is a signal which is 0 for n less than 0, all right. And so, what you can see here is that each, so this is the output pixel, okay. So, this yk, this is your output pixel, and these are your input or original, you can think of this as input pixels or original image pixels, okay. So, these are the original image pixels, and what you can see is that each output pixel is a combination, is a linear combination of several input pixels. So, you are not getting the crisp original pixels, but each pixel is sort of smudged, right. Each pixel is sort of smashed or combined along with other pixels, and that is what gives the blurring effect. That is when you combine, that is when you are not getting the clear individual pixels, but rather you are getting a combination of these pixels, that is x, y of 2, the combination of x of 2, x of 1 and x of 0. So, you are combining these pixels, alright, and that is what gives the blur effect. So, the linear combination of pixels is what is giving you the blur effect. The linear combination of pixels is giving you the blur effect, and therefore, the input output blur model can be represented as follows. Let us say you have a group of output pixels, that is, which you are representing by the vector y of 0, y of 1 up to y of, let us say, m minus 1, that is total number of pixels is m. So, you call this your output pixel vector. We are considering a single column of an image. So, this is your output pixel vector. This is equal to, well, h of 0, okay, h of 1 times h of 0, and so on and so forth, and this matrix has an interesting structure. This is, in fact, this is x of 0, x of 1 up to x of m minus 1, and the second row is h of 2, h of 1, h of 0, and of course, you can also have noise. Now, in addition, you can also have noise, but let me just ignore this for a little bit, okay. Just to simplify this model a little bit, although in technique, in practice, you can also have noise, or let us make this, let us add the noise, it does not matter, okay. And now what you can see is y of 0 is h of 0 times x of 0, y of 1 is h of 0 times h of 0 times x of 1 plus h of 1 times x. So it also depends, so it combines both x1 and x0. Similarly, y of 2 combines x0, x1, x2, so on. So each pixel is a combination, a linear combination of the pixel itself and the original pixel and some neighboring pixel, and that is what gives the blur effect. And this matrix which, so this is the output pixel, this is the original input pixel vector. We are considering, as I said, a single column of pixels. Okay, and this is basically your filter matrix. This is also known as a filter matrix because you are representing the blur by this filter, this linear, this filter is represented by this linear transformation characterized by this matrix. I can call this matrix as matrix H. This is your filter matrix or your blur matrix, and this filter which you are repeating along the low rows, this is also called the kernel, or this is basically your blur kernel. Alright. So I can represent the blurring effect in the image as this linear system. So the blur model can be the blur effect. In fact, this model can also be used to introduce blur, alright, to get that blur effect in images. For instance, if you want to give the effect of an object being in motion, such as a car being in motion, this linear transformation can be used, alright. So this can be used both ways, either to recover the original image from the given output vector y bar or given input vector y bar x bar. To introduce the blur effect, one can use this linear input output system model, alright. Now the point that in the problem that we are considering is the other way around, specifically that is given a blurry image, how to deblur it. Alright, and now once you formulate this problem, so this is your original image. Okay, I am representing a single column, although this can be easily extended to a two-dimensional original image, and this can be easily extended to two-dimensional, in fact three-dimensional images also, which is with nothing but video. That is, you have x-axis, y-axis, and in the time. Alright, so one can have three-dimensional blurring effect, so as to speak. So alright, so you can have original image, and this can be extended. I will just note here, can be extended easily to 2D images plus video. And therefore, how to reconstruct the original image? We know that. Now we have this model or output image y bar equals the blur matrix H x bar plus the noise vector. So this is your blur matrix, and to reconstruct the original image or to recover we now apply the least squares, alright, and therefore what we do is minimize norm of y bar minus h x bar square implies the estimate or the reconstructed image or the deblurred image is the pseudo inverse of h. We have not introduced this notation so far. Let me just describe this. This is nothing but H transpose H inverse H transpose y bar, where we are denoting this matrix by H dagger. This is known as H dagger equals the, we have already said this, this is acts as a left inverse, this is the pseudo inverse of H, okay, not the inverse but the pseudo inverse, this is the left inverse of H, and this x hat is now your deblurred or reconstructed image. This is your deblurred or reconstructed image, and therefore what you can see now is that yet another interesting applications of the least squares paradigm. It is a very interesting application. It can be applied, we have already seen another application, that is for channel estimation in a wireless multi antenna system. It can also be used for deblurring of images in image processing, and therefore reconstructing or recovering the original images. Alright, and therefore the least squares paradigm in general has many applications, several applications. It's one that arises very frequently, in fact in several different areas, signal processing and communication, and also other scientific disciplines. Alright, so we will stop here and continue in the subsequent modules. Thank you very much.